Today, we're going to pull back the curtain on our digital world. We're going to explore the hidden mathematical language that makes pretty much everything, from your phone to a rocket ship, work with just incredible reliability. You know, it all starts with a problem we're all familiar with. Bugs, glitches, crashes. Why do they even happen? Well, it's because we build these super complex systems using human languages and logic, which, let's be honest, can be fuzzy and ambiguous. But computers, they need absolute rock-solid precision. So how in the world do you bridge that gap?
The real root of the problem is ambiguity. When you tell a computer what to do, there can be literally zero room for misinterpretation. And as our systems get more and more complex, the chances for a tiny error just skyrocket. We need a better, more precise way to talk to our machines.
To solve that problem, we need a language of absolute precision. And for that, computer scientists turned to a field of 19th century mathematics that was designed for exactly this kind of rigor: set theory.
So it all begins with this one, simple but really powerful idea: a set. Now, the magic phrase here is well-defined. Unlike a vague collection like talented students, a mathematical set has zero ambiguity about what's in and what's out. This is the bedrock, the foundation for the precision we absolutely have to have.
And mathematicians came up with too many ways to create these perfectly precise collections. You can either list the members out one by one, that's called the roster method, or you can just state a clear, unambiguous rule that every single member has to follow. Both roads lead to perfect clarity, no confusion.
Okay, so once you have sets, you can start doing stuff with them. The first one is union. Just think of it like dumping 2 buckets of Legos into one big bucket. You just combine everything from all the sets into a single, bigger set. It's really that simple.
Next up, we've got intersection. This is all about finding the overlap. If you have 2 sets, their intersection is a brand new set that has only the items that were members of both of the original sets. It's just the common ground between them.
And finally, there's difference. This is basically just subtraction, but for sets. The difference between set A and set B is everything that's in A except for any of the items that are also found in B.
Okay, so union, intersection, difference. I know, these seem like pretty simple ideas, right? But how do they help us build flawless computer chips? Well, this is where these basic building blocks start to create something incredibly powerful.
Now, at first glance, this looks incredibly weird. I get it. But this is actually the set theory definition of an ordered pair, the fundamental concept that A comes before B. It might look overly complex, but this shows the kind of radical precision you need. In computing, you can't just assume order exists. You have to build it from the most basic logical pieces imaginable, using nothing but the idea of a collection.
And this level of precision lets computer scientists do something amazing called formal verification. Here's how it works. First, they describe the entire computer system using the ultra-precise language of Zermelo-Fraenkel set theory, or just ZF, which is really just a standardized, super rigorous version of what we've been talking about. Second, they state a goal, like this microprocessor will never ever produce a wrong answer, and they state it as a mathematical theorem. And third, they use a software tool called a proof assistant, one is named Isabelle, to mathematically prove, beyond any doubt, that the system is perfect.
And listen, this isn't just some niche academic idea. As computer scientist Lawrence Paulson points out, some experts actually argue that the usual ways we organize programming code can get in the way of creating perfect systems. They believe pure set theory gives them a more fundamental, more powerful foundation for getting it right from the very beginning.
So, does all this theory actually work in practice? Oh, absolutely. This isn't just a thought exercise. These proof systems are actively used, they're benchmarked, and people even compete with them to see which one is the most powerful.
So how do you test these systems? You don't give them simple problems. No, you throw major mathematical challenges at them, like proving something called Ramsey's theorem, which is a deep and famously complex result about finding order inside of chaos. If a system can handle that, you know it has some serious logical horsepower.
And this table right here shows the results. It's comparing 3 different proof systems all trying to crack Ramsey's theorem. Now, look at Isabelle. That's the system using set theory. It required the fewest supporting arguments, or lemmas, to build its proof. What that means is it was more direct, more elegant. It also had the fastest replay time to re-verify the whole thing, just over 2 minutes. And that is crucial, because it shows the proof isn't just correct, it's efficient. A system built on this fundamental math can clearly hold its own and even outperform other highly specialized tools.
So let's bring it all about together. We started with some abstract 19th century math, and we ended up with the technology that's literally in your pocket right now.
It all began with one of the simplest ideas in all of mathematics. Just a well-defined collection of distinct objects. That's it.
And from that one simple, perfectly precise foundation, we build layer upon layer of pure logic. This is what allows us to construct systems so complex we can barely imagine them, yet so reliable that we bet our lives and our fortunes on them every single day.
So the next time you use any piece of technology, just remember you're not just interacting with silicon and code. You're interacting with the elegant, invisible structures of mathematics. And it kind of makes you wonder, right? What other simple math is secretly running our world?